In this video, we introduce our AAAI 2023 work, Tracking and Reconstructing Hand-Object Interactions from Point Cloud Sequences in the Wild. In this work, we tackle the problem of online pose tracking and reconstructing hand-object interactions. From a live point cloud sequence, given the segmented hand and object along with a noisy initial hand pose and object pose. Our method can jointly track hand-object poses and reconstruct their shapes. Different from previous work, we don't assume known hand and objects and can track without knowing the ground truth object mesh. Let's first look at our online reconstruction results on the unseen real dataset, DEX-YCB. We show the input point cloud, and the output reconstruction in the camera view and in a rotated view. We also overlay our output on the RGB image. On the HO3D dataset, we also show results with high-quality tracking and reconstruction. Our algorithm runs at 9 frames per second. Our method can handle object instances from unseen categories, for example, a box. Even under heavy hand-object interocclusion, our method can handle well. For learning to track and reconstruct human-object interactions in the wild, the main challenge is the lack of large-scale diverse data with full annotations. To mitigate this problem, we generate a realistic and diverse simulated dataset, which we call SimGrasp dataset. As shown here, SimGrasp contains hand-object interaction sequences covering diverse hand and object instances, as well as dynamic grasping motions. In total, SimGrasp is composed of more than 180,000 frames, 600 object instances, and 100 hand shapes. We implement a structure light-based depth sensor simulator to generate realistic depths. Compared to perfect depths, our simulator can capture realistic noises and artifacts that exist in real-world point clouds and thus significantly minimize the Sim2 real gap. In addition to the data challenges, the learning-based hand tracking method is extremely underexplored. Previous learning-based works mainly focus on single-frame hand pose estimation, which can't guarantee the temporal pose coherence and suffer from large ambiguities under the heavy occlusions in hand-object interactions. Our work, for the first time, proposes a point cloud-based hand pose tracking network, namely HandTrackNet. The first contribution of HandTrackNet is to improve the canonicalization technique. To reduce the visual complexity of the input point cloud, previous works first use PCA to compute an oriented bounding box and then use it to canonicalize the hand, so that the global pose of the hand becomes canonical. However, this canonicalization technique will fail in hand-object interaction scenarios due to heavy occlusions. In this work, we propose to leverage the temporal continuity to canonicalize the input point clouds. Given the hand joint positions from the last frame, we fit its global pose and use this to canonicalize the input point clouds. To further leverage the temporal continuity, we propose to only regress the interframe residual motions of the hand joints, which significantly eases the regression learning. Altogether, our proposed HandTrackNet jointly canonicalizes the input and output spaces, thus greatly facilitating the network learning and improving the generalizability. Finally, we observe that hand-object pose and reconstruction need to be physically realistic, for example free from penetration or object floating in the air. We thus propose a full pipeline that jointly tracks and reconstructs hand and object, which enables optimization-based hand-object reasoning. Here we provide a walkthrough of our pipeline. Prior to tracking, our system needs an initialization phrase at frame 0. To obtain hand template, we use HandTrackNet to predict the hand pose, J0 pred. Given the pose, we fit a mano hand template by minimizing the difference between the bone lengths of J0 pred and those of the template, yielding a hand shape code, beta. For object, we first canonicalize the object point cloud using the initial object pose. Then we optimize the object shape code of deep SDF to find an SDF that can best fit the canonicalized object point cloud. Note that our method can also update both hand and object shapes during tracking, but we skip the details in this video for simplicity. After initialization, our system performs online pose tracking and reconstruction for the hand and object. For hand, at each frame, HandTrackNet outputs hand joint positions JT pred. Then, to further obtain the hand mesh, we introduce the inverse kinematic network that converts the joint positions into mano pose code. For object pose tracking, we simply perform online optimization based on depth to SDF conformation. These two modules can run in parallel and reach a speed of more than 25 fps. Finally, to enforce the physical realness, we construct several prior energy terms using the hand mesh and object SDF and then refine the hand pose via optimization. Here are some quantitative results. Compared to the state-of-the-art point cloud-based pose estimation network, hand-folding net, and depth-based network, virtual view and A2J, together with an optimization-based hand-tracking method fourth, we have the lowest mean per joint position error on both HO3D and DEX-YCB datasets. Compared to state-of-the-art point cloud-based object pose tracking method, CAPTRA, we have higher 5° 5 cm accuracy on both datasets. To conclude, in this work, we propose a large-scale dynamic Hoi simulated dataset SimGrasp, that captures sufficient diversity and realistic sensor noises and thus supports direct Sim2 real generalization. For the first time, we propose a point cloud-based hand-tracking network HandTrackNet that outperforms all the previous single-frame networks. Furthermore, we build an online system that jointly tracks and reconstructs hand-object interactions. Our intensive experiments show that our method achieves the highest performance on both DEX-YCB and HO3D datasets. We have released our code and data in our GitHub repository. Thank you for listening.